Hello everyone. Today we are going to look at a particular problem which says that a statement, basically, power set of natural numbers is uncountable. So we know that natural numbers are countable. I mean, the countability is basically we are trying to frame the idea of natural numbers because we can count that 1 2 3 4. So we say that a set S is countable. Okay, let us write that S is countable if there exists a bijection from N to S or S to N or something. So if there is a bijection from S to N, natural numbers, so then only we can say that S is countable. But we can reduce this thing to two sub cases. Like we can reduce this to S is countable if there exists a 1 function from S to N. So there we don't have to go for a bijection now. We can see that S is countable if there exists a 1 function from S to N. It is because if A and B are finite sets, then if F is a function which is 1 to 1 to B, this implies the cardinality of A is less than or equal to the cardinality of B, right? So if the other way, you can say something like 1 2 3 and something like 4 5, you will not be able to make a bijection. So whenever you have to map every value, definitely two value must share a point in the codomain. So that means a 1 function is not possible if cardinality of A greater than cardinality of B. So that means, so that ideas will carry on to the infinite case too. So what we can say, the cardinality of S, analogically we cannot say the less than or equal to symbol, but the notion here, cardinality of natural number, that means, right? So that must be countable. That's the idea comes from that. We should need a different proof anyway, but just an idea. We can see that S is countable if there exists a 1 function from S to N. Similarly, S is countable if there exists an onto function from N to S. Same idea here. If A and B are finite sets, and if F is onto function from A to B, then definitely the cardinality of A must be greater than or equal to cardinality of B. Here we have cardinality of N is greater than or equal to cardinality of S, which gives best logic to understand the countability of S here. So we can reduce these things. So basically what we are address, we need a bijection from N to S or S to N. So this is what we say countability. If it is not possible to exhibit such a bijection, we say that it is uncountable. So we have to understand what is a power set of natural numbers. So we know that natural numbers are, we starts from 1 2 3 4 5, like that is goes on, because it is the numbers we use to count the objects, right? Now power sets means what? Power set means it is the collection of subsets of natural numbers. For example, singleton sets, everything will come, and some finite subsets will come, and also infinite subsets like even numbers, odd numbers, prime numbers, everything will come. So the list just goes on, right? So we are going to prove that this is uncountable. That means we cannot make a bijection between n and power set of n. So what is our basic idea is to prove that there is no bijection, there is no bijection between n and power set of n. Okay, so for this we will use a basic lemma provided by Cantor, George Cantor. So that is very interesting one. So let us write that in this way. So this is a, we can call a lemma, right? Because we are using this for to prove our main observation. There is no bijection between n and power set of n. So the lemma says like this. Let A be any set, then there is no onto function from A to power set of A. It's a very simple statement. Let A be any set, then there is no onto function from A to power set of A. So how do we prove this one? So we use the method of contradiction. So we assume that f be such an onto function. That means f is an onto function from A to power set of A. That is, f is onto, f is from A to the power set of A. Because f is onto, what we can say, for every y belongs to power set of A, there exists an x belongs to A such that f of x equal to y. So for every element in the codomain, that means P of A, I will have a pre-image in the set A. That's what I have assumed here, right? Okay. So now my idea is I want to develop a contradiction, and for that I am particularly picking a subset of A. I will show that there is no pre-image in A. So that's my idea. So so I can try to develop such a subset, right? So let me take y equal to x belongs to A such that x does not belongs to f of x. Seems to be little confusing, because this is a collection of elements of A. Of course then is a subset of A, which satisfy this particular condition. What is that condition? X does not belongs to f of x. So in order to clarify your doubts, we can take a function. I mean, suppose I'm not considering the onto functions, one function, just a function from a to power set of a. So let it be something like, for example, let me take a is equal to 1 2 3, and I mapping from I know, and so I map a to the subsets of a, right? For example, I am mapping 1 to 2 3 and 3 to 1 3 and 2 to also the 1 3, no problem. Here you can see that this is what we have, f of 1, right? This is f of 3, this is f of 2. So look at can we consider construct the set y here? Yes, because what is y telling? X does not belongs to f of x. Here is 1 belongs to f of 1? No. So 1 does not belongs to f of 1, because f of 1 is just 2 3, so 1 is not in that. Here is 3 belongs to that? Yeah, 3 belongs to f of 3. Is 2 belongs to 1 3? No. So 2 does not belongs to f of 2. So from this I can construct my y. My y is all elements which does not belongs to its function value. So that means 1 and 2. 3 is not there, right? So so this way we can consider this is a well defined set. That's what my point. Okay, so here in generally, so I'm just erasing these things. So we have understood we can construct this set for a function from a to power set of a. So for this particular function I am considering this y. Of course we have seen that y is a subset of a, that is it is an element of power set of a. Okay, now by our assumption there exists an x naught belongs to a such that what I can say, f of x naught equal to y, because for any y, for any subset I taking from the power set of a, element of power set of a, I will get an x naught. That's what the onto-ness of this function. So what I can say, so there is an x naught belongs to a such that f of x naught equal to y, this y. Now here is the point. My question is x naught belongs to a? I mean x naught belongs to y? Yeah, that's my question. Is x naught belongs to y? So because an element from a and y as a subset of a, I have two possibilities. So either x naught belongs to y or x naught belongs to y. These are the only possibility, right? Because x naught being an element of a, definitely these are the only two possibilities. Let us take what happens if x naught belongs to y. This implies x naught must satisfy the property of a the set y. That means x naught does not belongs to f of x naught, and you know that f of x naught is equal to y. That's what we can see here. That means x naught does not belongs to y. So this feels absurd because x naught belongs to y, which implies x naught does not belongs to y. So that possibility is very weird. So let us look at what happens if x naught does not belongs to y. That means what? X naught is not satisfying the property of y. That means the complement x naught belongs to f of x naught, which is again x naught belongs to y. That means if you take x naught does not belongs to y, you are getting x naught belongs to y. That's also absurd. So basically we are making a contradiction by picking this particular subset of A. Okay, so that is, there is no onto function from A to power set of A for any set. So in particular, what we can say, let me take my A to be the natural numbers. So if you take A, the natural numbers, what can I say? There is no onto function possible from n to is power set of n. So there is no onto function possible. That also avoids the possibility of bijection, because bijection is an onto function, right? That means there is no bijection between n and power set of n, which implies power set of n is not countable. This implies it is uncountable. Thank you for this. So if you have doubt, you can ask in your comments. Yeah, so thank you, bye.